Hey, all you cool cats and kittens. No, I'm just kidding. I'm not Carol, it's Mrs. O'Brien. Hope you guys are doing well today. Make sure you drop in for office hours if you've got questions. I am trying to get things updated in the grade book. It's slow going because there's lots of emails to sift through just to make sure you guys are feeling supported with what you're doing right now. So please be patient with me. It's a big learning curve for all of us and try to manage our day and what's going on. Today we're taking a look at vectors in space. So we're going to look at all the things that we did with 2D vectors and then take a look at an application of them in 3D. So let's go ahead and get started. Ordered triples can represent vectors. And remember, when we're writing vector notation for our values, ordered triples become pointy brackets for our vectors. When we're talking about just regular points, that's not going to change. We should have our curved brackets here. So when we're talking just about the initial points, we're going to have our regular smooth curve. That's our ordered triple 0, 0, 0. And our point P, which is X, Y, and Z. That's our ordered triple. That gives us the vector from O to P. Remember, direction matters. And now we're going to institute our pointy brackets, X, Y, and Z. And remember, we found vectors by taking the terminal minus initial. Remember, that's terminal minus initial for all of our points for X, for Y, and now we're going to do that for Z. And those are going to give us the X, Y, Z components of our vector. And regardless of where that starts, whether it starts at the origin at 0, 0, or if it starts elsewhere, we're going to be able to look in terms of what's happening as we compare things along the X, Y, Z axes. And putting it in that component form already brings things back to the origin and will construct another vector that's parallel in the same directions. So let's take a look at what that looks like in 3D. So I popped open GeoGebra and just put a couple points in. Here we've got the point 0, 0, 0 at the origin, and then I've got another point -2, 2, and 3. So -2 in the X, 3 in the Y, so I'm up here, and then we're shifting 3 units up. So you've had practice drawing in those parallelograms. Here's what that looks like from lots of different directions. And you can see our vector U right there. It's going from A to B. And we can switch this around. We can rotate for a while, but let's go ahead and change A and see what that looks like. Let's make this 1, 1, and 1. And notice how it shifts it up. Let's get rid of that. Now we are completely above that plane. And you can notice what's going on there. So we've got terminal minus initial, which is why our vector here is represented as -3, 1, and 2, because it's terminal minus initial, terminal minus initial. And we've had some practice with that. We can also talk about things in terms of their unit vectors. So the unit vector I, again, was how much it's going 1 unit out in the X direction. Vector J is how much it's going 1 unit out in the Y direction. And vector K is how much it's going 1 unit up in the Z direction. So those are our standard unit vector notations, and I can write it as vector standard unit vector notation by having v sub 1, v sub 2, and v sub 3 be scalar multiples of all of those unit vectors. So if it's v sub 1 units in the I, v sub 2 units in the J, and v sub 3 units up. That's how we can use our unit vector form. There's a couple important things that you need to get down, and these are in your book. You can also pause the video whenever you want and just write them down. But these are some of our important aspects about vectors in space. Two vectors are equal if and only if their corresponding components are equal. That also means if the corresponding components are equal, then the two vectors are equal. Number 2, the magnitude or length of a vector, so this is vector u, has its 3 components, and it's the exact same way we found magnitude in 2 dimension. We're going to take the square root of u sub 1 squared plus u sub 2 squared plus u sub 3 squared. And you can do this given the vector itself or from 2 points. And this would be the difference of the x's squared, the difference of the y squareds, and the difference of the z squares. Terminal minus initial. Then we've got our unit vectors, and we can actually find the length of a unit vector. So thinking back to our 3D vector that we have, I can find the unit vector itself that's representing all of these by taking the actual vector and dividing it by the magnitude. I can take the sum of 2 vectors and perform vector addition. You guys did this a lot when we were doing our map projects of where you projected your life to be. I bet none of you guessed this, which you didn't because I graded them all. But we're going to take the sum of the horizontal components, the sum of our y components, and the sum of our z components, those 3D components right there. Second to last one, scalar multiple. It's pretty intuitive that if I am taking a scalar multiple of a vector, I need to multiply each of the 3 components by that scalar because it's growing in all 3 directions. And last but not least, we've got our dot product. Our dot product is going to give us a numerical value. It is not going to give us a new vector. So the dot product of u dot v is the product of the x components plus the product of the y components plus the product of the z components. So let's practice a couple of them. Your first example says find the component form of magnitude of vector v having the initial points of 2, 4, 1 and terminal points of 3, 5, 2. So component form, that means I've got to take the terminal minus the initial. So I've got 3 minus 2, 5 minus 4, and 2 minus 1, which gives me the vector v's component form of 1, 1, and 1. It also asked us to find the magnitude of the vector, so we're going to go ahead and take the square root of 1 squared plus 1 squared plus 1 squared, which gives us the square root of 3. Remember, my pre-calc friends, that this is an exact value. This does not need to be in a decimal because this is the actual answer. Alright, find the dot product of these 2 vectors, -1, 3, 5, and 0, 4, and -2. So to take the dot product, we're going to take the product of the x component, the y component, and the product of the z component and find their sum. So -1 and 0, 3, 4, and 5 times -2. So of course we get 12 minus 10, which gives us 2. And that's it for the dot product. In order to find the angle between the vector, it's the exact same way that we did it in 2 dimension, but we're going to do it in 3D. So we're going to find the cosine of that angle by taking the dot product of the 2 vectors divided by the magnitudes products. Remember, the dot product of the 2 non-zero vectors of any angle between the vectors is 90 degrees when the dot product is 0. Those vectors, again, were called orthogonal vectors, and Batman and Robin knew the difference between the 2 of them. For instance, our standard unit vectors are all orthogonal to each other. So it says find the angle in degrees, minutes, seconds. So degrees, so take a second and make sure your calculator is in the right mode. It needs to be in degrees and not radians. Between 4, -1, 3, and vector v, which is 0, 1, and 5. Pause the video and double check and see if you get the same answer that I do. So we're going to go ahead and plug it in the formula. Cosine of theta is 4 times 0 plus -1 times 1 plus 3 times 5 divided by the square root. This is giving us the magnitude of u, 16 plus 1 plus 9 times the square root of 0 plus 1 plus 5 squared, so 1 plus 25. So that gives us the cosine of theta is equal to 14 divided by the square root of 26 times the square root of 26, which works out very nicely for us because that is 14 over 26, which can be reduced. So we get the cosine of theta is 7/13, and of course to find theta we're going to take the cosine inverse. So once you have that angle in your calculator, then in order to get it into degrees, minutes, seconds, we're going to go second, and then we want angle. So this is right above your apps button, and that's why we're hitting second. So we're going to hit the second and then the apps button, and then we're looking for this symbol, changing it, our answer, into degrees, minutes, seconds. And what you should get is 57 degrees, 25 minutes, and 16 seconds. If you have 15.707 seconds, even better. But that's what you're going to get given a shot for homework tonight. Here's that homework assignment. It's going to be posted on your Google Doc, and let me know if you guys have any questions. Be sure to check your answers from the previous night's homework and let me know what you need help with. Have a great day.